In this video, we're solving a classic optimization problem where we're trying to minimize the surface area of a can. So I'm just talking about a typical food can here. There's a top and a bottom. Both of those are circular. And then I have the curved surface wrapped around the outside of the can. And we have a fixed volume that we're interested in containing in this can, but I want to minimize the amount of material it takes to construct it. So it's the surface area that we're minimizing here. In the way this question is posed, we're asked to find the relationship between the height and the radius, giving us the minimum surface area. So just to start things out, I think I'll write down an expression for the volume of this can and an expression for the surface area. And the volume is going to be the area of the base, which is pi r squared, then multiplied by the height. The surface area is going to be the area of the top and the bottom plus the curved side of the can. So the top and the bottom each have an area of pi r squared because those are circles, and I have two of those. So I get a 2 pi r squared plus the area of the curved part around the outside of the can. And what you have to do here is visualize cutting this thing vertically and unrolling it. If you do that, the length of the resulting rectangle is going to be 2 pi r. In other words, the circumference of the circular edge of the can. And then the height is still just h. So we have an expression now for the surface area, and we're trying to minimize that. Unfortunately, it's expressed in terms of two different variables, r and h. And this is where we need to go back to the volume formula and solve for one of those variables in terms of the other, so we can do a substitution and get the surface area expressed in terms of a single variable. Now, because r is squared in the surface area formula, I think it's best if we solve for h and just sub that out in terms of r. So I'm going to take that volume formula and solve for h. Remember, v is a constant here. So h is going to be v over pi r squared. And then I can replace the h in my surface area formula with v over pi r squared. Now notice what I did there is I just wrote s of r. That's not a multiplication. What I'm trying to emphasize there is that this will give us the surface area as a function of r only. So I have a 2 pi r squared for the first term. And then for the second term, making the substitution on h, I have 2 pi r times v over pi r squared. And the pi's are going to cancel there, and one factor of r is going to cancel. And so my surface area as a function of r only is going to be 2 pi r squared plus 2v over r. So everything is constant in there except for r. Remember, v is a fixed value as we try to minimize the surface area. So if we're going for the minimum value of the surface area here, we're going to find that by taking the derivative and setting it equal to 0. So I want to find an expression for s prime of r. When I differentiate the first term, I have an r squared. Again, this is an r derivative. So I'm going to bring a 2 out in front and subtract 1 from the original exponent, and I get 4 pi r. In my second term, the 2v is just a spectator. What I'm differentiating is 1 over r, or r to the negative 1. And that differentiates to negative r to the negative 2, but we can clean that back up in terms of positive exponents. And I find that my derivative of the surface area function is going to be 4 pi r minus 2v over r squared. So again, we're looking for the value of r where this is equal to 0, and that will put us at the minimum value of the surface area function. So we have to solve for r here. And I'm going to start by multiplying both sides by r squared. And this gives me a 4 pi r cubed minus 2v is equal to 0. And we can divide a 2 out of that. And I end up with 2 pi r cubed minus v is equal to 0. So we're going to move the v over to the other side and divide by 2 pi and cube root the result. So again, on the right hand side, we'll have a v over 2 pi and then we cube root it. So I end up with the cube root of v divided by 2 pi. So there's the necessary radius of the can that's going to minimize the surface area. And that's written entirely in terms of that constant volume value, v. Now what we need to do is find the h corresponding to this value of r, because we want to find a relationship between h and r when the surface area is at its minimum value. So I'm going to take that r and plug back into this relationship up here where we solved for h in terms of r. So h is going to be v divided by pi times r squared. So I'm taking the cubed root of all this stuff and squaring it. I could write that all as an exponent of 2/3. So now I can turn this all into a single fraction by multiplying by the reciprocal of that fraction in the denominator. And I've got a v times 2 pi to the 2/3 in the numerator divided by pi times v to the 2/3 in the denominator. And we keep simplifying here. So the only number I have in there is a 2 to the 2/3 up there in the exponent. And that's the same as saying the cubed root of 2 squared, in other words, the cubed root of 4. And then I have a v in the numerator and a v to the 2/3 in the denominator. If I subtract the exponents, I get v to the 1/3, in other words, the cubed root of v. And then I have a pi to the 2/3 in the numerator and a pi in the denominator. And that leaves me with a cubed root of pi in the denominator. In other words, pi to the 1/3 down there. So that's convenient because I can turn this all into a single cubed root. That's the cubed root of 4v divided by pi. So now we have two similar expressions for r and h written in terms of the fixed volume v, and it's time to compare these two things in some meaningful way. And if we take a ratio of these two dimensions, the v's are going to cancel out and just give us some proportionality between h and r. So we'll just go ahead and compute h divided by r. So that gives me the cubed root of 4v over pi divided by the cubed root of v over 2 pi. Well, the quotient of two cubed roots is just the cubed root of the whole quotient. So I'm just going to write it that way from the beginning. And so my numerator there is going to be a 4v over pi. That comes from our expression for h, the cubed root of 4v over pi. And then my denominator is going to be a v over 2 pi. So I multiply by the reciprocal to clean this thing up, and I end up with a 4v times 2 pi in the numerator and a v times pi in the denominator. And now the v's are going to cancel out and the pi's cancel out. And I end up with the cubed root of 8, which is a really nice answer. The cubed root of 8 is just 2. So we can summarize the relationship between h and r that minimizes surface area here as h equals 2r. And it may be even better to write this as h equals d, where d is the diameter of the top of the can. So this is one case where the right answer turned out to be a really beautiful symmetric answer. If you build a food can so that the height is exactly the same as the diameter, you get the minimum amount of material required to construct that can. In other words, the surface area is minimized when the can has a square profile. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the ZaxLab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zaxlab, and best of luck on your math and physics journey.